Okay, let's continue our discussion today. So, well, after talking about saturation, so one of the key important parameters other than, I want to make a correction on the previous slide, which previous lecture, which I made a mistake on highlighting the output resistance. So, GM B pi R pi. So GM, the key parameter is GM. GM is VT over ICQ. And R pi is GM is beta over GM. And then finally, output resistance, there's an additional parameter which is early voltage. So in finding this, you will then need three more parameters, which is two more parameters, beta and VA. So this will typically be provided to you in a device model. So you will then know that your early voltage, what is the early voltage, and then we can calculate output resistance as well as allow us to find R pi, beta and VA. One of the key important things you need to understand is that I want to just extend a little bit on the discussion of early effect is that when WB decreases, what happens is that this is called a narrow base device. The reason we want narrow base, of course, is then it would then lead to yes? Oh, sorry. Yeah, correct. Okay. I'm running time. B, C. Okay. So when you narrow down the base, a narrow base device will then give us one of the key parameters we want to obtain is actually increase of beta. So this will then allow us to have a good current gain because you narrow down the base. But then the side effect is that your VA will also decrease because it will make the slope, it will make it early effect more significant, more prominent. You think about early voltage when VA, if I say VA approaches infinite, that simply means that no early effect, right? Because my voltage is at the ultimate end, so you don't actually see it. But when early voltage shrink, that simply means that your slope actually increases, so more significant early effect, right? Modulation effect. That would happen when base decreases, base width decreases. The other thing is that the other part that would affect this is base doping. So to increase beta, remember what determine beta or determine IS is inverse proportional. If I'm writing down IS. If you're writing down IS, it's inverse proportional to NBWB. So let's say if I want to increase my IS, one is reduce WB, the other is reduce MB. So let's see what happens when you reduce MB. This is the lighter base. If I want to make a description, is that if I'm using a lighter base, the base is lightly doped. So this will also increase my beta if the other structures remains the same. My emitter collector remains the same. So what is the impact? What do you think? You think your early voltage will what? What do you expect? It will increase or decrease? Remember, the base width modulation is the depletion. So by applying the same voltage with a lighter doping, meaning that it will deplete more or less. Lighter doping will then deplete more, right? So when it depletes more, it will be more significant. So this will also decrease, meaning that your output resistance will decrease as well. So this is the same direction. If you want to increase your beta, beta and early voltages are sort of like a trade-off. If you wanted to increase your beta by engineering your base, these two directions will both lead to more significant early effect or reduce of output resistance. Okay? So let's come back to saturation. I want to highlight one important thing. So one of the key, what you need to learn about saturation is, once again, let me summarize it, is that it will then lead to IC reduce in saturation as VCE decreases. As VCE decreases. And when will you see this? In typical cases, we'll see this when VCE is smaller than VCE set. So what defines VCE set? VCE set is we want to know the difference between base and collector voltage. So base and collector voltage will be VBE minus VCE set. So this will be somewhat about 0.4 volt. And this voltage come about because of the exponential nature of that equation. So if you just think about, it will depend on VT, of course, but because of the exponential nature, if it's close by 400 millivolt, then you will see significant difference in the gradients of d and dx. So that is why typically, if you want to define VCE set, we'll typically define as VBE on minus a 0.4 volt. So let's say if my VBE on is set to 0.4, then VCE set is typically at 0.4 volt. So this will also typically be given to you in the question. So these are also device parameters will be given to you. So VBE on and VCE on are both limiting where the operation region are. Okay, so this is typically we use to define whether it's in active or in saturation in circuit analysis, not describing what really happened in the dial. So real saturation and circuit this is typically referred to as the circuit saturations when you see the difference in collector current. Okay? So the next thing I want to spend a little time on is we still have 2 more topics. One is reverse active. I'm only going to talk about this very briefly because, as I said, this is mainly because you connect to your circuit wrong. But let's spend a little time and discuss what's the definition of reverse active and what happens. What is it? Behavior. So let's think about reverse. In reverse active mode, what it means is that I have VBE in reverse, VBC forward. I have one junction for the other junction forward, the BC junction forward, and BE junction reverse. So what happened is that you also still look at the minority carrier concentration distribution. What happened is that it will look a little bit like that, but you then have something like this. So this is E, B, C again. So I will then form my BC junction. So I'm just going to highlight the doping concentration once again. So let's say this is 10 to the 19th. You already dope your device when the device are already made, right? So this is 17, this is 16. This is N, B, and C. And E. So what happened is I'm raising this minority. So this will be very similar to that, just in reverse. So I'm reverse biased this junction, so this will be down to 0. So then my MP at WB will be the highest MP0 exponential. Okay? So basically what happened is that your collector current, or I should say it becomes emitter current. The emitter current, if I'm drawing my emitter current in this case, this is my emitter current. So my emitter current will then become IS exponential VBE over VT. So it's identical to active, inactive, the IS. It's the same as IC in inactive. So there's no loss in this, in creating the electron current. So your electron current is the same. So you actually have the same DN, it's just reverse direction. And this is the electron current component. Right? The electron current is identical because your base is identical. But the only difference is that what is the cost? The cost of for biasing this junction is that I need to supply a lot of whole current, a lot more. Right? So then you expect that you would then have a, this is your whole density, so this would then create a whole current. Where does this whole current come out? This whole current will depend on inverse ICL, I should say LP. Because we don't have a narrow emitter or narrow emitter, we don't have a very narrow emitter, therefore you cannot use WC because WC is very, very long. Remember, it's down all the way down to the well. So you have to use diffusion, the diffusion, we call it diffusion length of holes in collector. But that's not very important. One of the key important thing is this. Because we have a very lightly doped collector, therefore your IH will be much, much larger. IH in active. Remember, the IH in active is inverse proportional to NC. Remember our exercise, right? So this will be much, much larger because collector is lightly doped. Therefore, you would then have very poor beta. Typically, what happens, if you look at this, what is beta? If you think about that, when I talk about saturation, is that beta is a portion of the red part against the green part, the blue part. So as long as in original operation, remember I have a large red part, which would then create a large collector current, electron current. I want large electron current, smaller whole current. In this case, I have a larger electron current. So what happens is that my electron current component will be larger than whole current component. This would then lead to typically a beta. This R stands for in reverse active, will be typically lower than 1. So this is actually what we actually don't want, is because, as I said, current gain is a gain. You're not getting anything. You're getting less than 1, meaning that whatever you put in is larger than whatever is being taken out. Okay, so if I'm operating in reverse active like this, I can still operate in reverse active. Let's say, it's very hard because it typically wouldn't work this way. So let's say this is forward active. This is forward. In reverse, what happens is that you flip the device. So you misrepresent it will be something more like this. So if I'm putting this at a high voltage, say, let's say VCC, this is 0.8. If I operate this way, this is 0 volt. So this is called a reverse active. This is forward. So BC larger than 0, BE smaller than 0. That's called the reverse. So in reverse active, my output current is this, right? This is my output current IO. So whatever my put in, the main reason is that the IO is identical, but whatever I'm putting in, the IB is much, much larger than if I'm operating in active mode. So I'm paying too much input. Therefore, I will be getting a gain of less than 1. This will be defined as IE over IB in reverse active. Okay? So for current gain less than 1, it doesn't really help you anything. It doesn't, you're paying too much, and then it will then lead to very poor transistor or amplification performance. Therefore, this is typically, you want to avoid that, or you want to avoid misconnecting your circuits. Okay? Yes? Which one? NP 这里这边哦，你说这边啊，这边应该是 BC 啦，对，你说对，应该是 BC。不是，就是如果你反过来操作啊，所以你反过来操作 BC 就是 BE 啊，那纯粹只是命名的问题。对，应该这边是 BC 啊，因为我 define 这边还是叫做 BC 啊。对，这边是 BC 对。So this is MP0. I'm just simply saying that it's because anyway, if you're forward biasing a junction, the forward biasing would then dominate your highest minority carrier concentration at the boundary. So you're right, this is VBC. Identical to if this is when you assume VBE equals to VBC when you're operating in the reverse direction. So you still apply 0.8 at VBC. So comparing forward and reverse, if I'm setting this to 0.8. So if I'm putting an identical device but simply flip emitter and collector and apply the same type of biasing on top, then it will be identical. The current itself, the current level will be identical. The main reason is because your base is the same. Remember the emitter, the collector or emitter current, because this is reversing, but the main current passing through the, if you're operating in we call the active mode, even for reverse or for active, doesn't really matter. Whatever the current, it will depend only on the base structure when we derive. Remember when we derive IC, it only depends on base structure. So because the base is identical, it's supposed to be the same. It should be follow the same. The IS is the same. This is what I'm trying to say. Okay? But you're applying, you're using BBC as VBE when you flip the emitter and collector. Okay? Good? So we have one last topic to discuss to wrap up the whole chapter. So that's PNP transistor. So if we want to talk about a PNP transistor, in a PNP transistor, what actually happened is that it's actually, I'm just going to talk about active. It's the same. So you have P and P transistor. So the main difference is that we're going to reverse the types. So when I forward bias PN junction, what happened? This will be my EBC. So when I forward bias EB junction, this will then lead to the main current will be dPdx through the base, and then my base current will be dNdx, will be depending on emitter's electron current. So the collector current will be determined by dp dx in base. Therefore, it will be proportional to, because it's whole current in base. So it's whole, I should say whole, this simply say whole diffusion. dp dx is just short for whole diffusion current in base. Therefore, because it's whole, so it depends on hole's mobility, and the diffusion structure will then allow us to set the doping level will be inverse proportional to MB, and the distance is WB will then determine inverse proportional to the gradients. Okay, so that's what we get collector current, and the base current is determined by dn dx in emitter. Okay. So for dn dx in emitter, what happened is that would then be proportional to mu n because it's electron current. So it's electron diffusion in emitter. Let me write it down. It's electron diffusion in emitter. Therefore, it will be proportional to its mobility because it's electron current, and inverse proportional to emitter doping and emitter base. Okay? So as I talk about the current gain for PNP transistor, it will then be the ratio between ME over MB, WE over WB, mu P over mu N. Right? So what happened? Why is it? Why doesn't we pick the PNP transistor? So for the same discussion, if I have the same doping level as an NPN counterpart, so this will be the same thing, the same doping level, and the same WE/WB ratio. If this remains the same, if these are the same to the NPN counterpart. So if I make an NPN with the same ratio and emitter base ratio and emitter base doping concentration, I want you to compare a NPN. I should use the PNPN. So if I want to compare the two, what does the ratio depend on? All the device structure, doping concentration are the same, so you cancel each other, and you get a mu P over mu N squared. Okay? So what it means is that it gives you an attenuation about 1/4 to 1. This is about 1/4, or depending on the ratio. If the ratio is 1/3, then you get 1/9. So that means that if I'm assuming that, so 4 mu P over mu N equals to 1/2, and beta, for beta NPN with the same structure of 100, your beta PNP will be 25. The same structure, the same technology, you're making the same structure, same doping, nothing changed, but simply because the type of carrier the main reason is that my main conducting current carrier is whole. The price I pay is electron, because electron move faster, therefore it would then lead to a discrepancy. I should say twice penalty on the ratio between base current and collector current. Therefore, you will then have much less current gain in a PNP transistor. Okay? But then we can still construct its model. Its model will be the same as an NPN transistor, but let me see if what I want to talk about. Okay. So the operation of an NPN transistor, it will be more like this. A PNP transistor will be more like this. For biasing this junction, I can still have it operated this way. And then this is typically how you operate as a common emitter, because this will be at a high voltage. This will be VCE. This will be your VBE. And this is my collector current. So collector current will still be my output current. So this is when I forward bias this junction, reverse bias this junction. This is for a PNP. In a active. In its active mode. Okay? So that's how we do the biasing. But the equations are basically the same. If you want to write down the large signal equation, it will be, there's simply some little correction on the voltages. If you want to make your voltage positive, it will be EB as positive. I should say this is VEB. This is VEB. If I'm using the positive voltage to define, this will be VEC, because this is E, this is C. So it will be VEB over VT, 1 plus. For the early effect correction, it will be the same. Instead of, if you want to use all positive numbers, just use EB and EC rather than CE. That's just to make sure that your voltage is always reflected as positive. Okay? So I would like to go through a simple example now, so that you get a sense as to how does one analyze a PNP transistor in circuit. So let's go through maybe two. We might have time for 2 examples. Okay? So let's go through an example of a PNP transistor. This is also a common emitter stage. It's just I'm using a PNP instead of a NPN. So for common emitter operation, you simply, this will be my highest voltage. This is V. 2.5. And then this will be my collector resistance, because I'm in reverse. And let's say if this is the output, this will connect it to ground. If I'm using a PNP transistor, and this is connected to a resistance and then a fixed bias of 1.5. So if I give you this circuit, I would like you to do 2 things. One is to find out, first of all, to find out ICQ, your operating point. And second is to construct the small signal model. Okay? So to construct a small signal equivalent circuit. So first of all, I would like to, I need to give you the device parameters. So in this case, we're going to use the constant voltage model. So for Q1, instead of have VBE on, we have VEB on, which is 0.8 volt. So instead of using an exponential model, we're going to use the constant voltage model. And then, of course, there's the beta. As I said, beta will be a lot smaller, so I'm going to use 25. We have a very small beta. Okay? So first of all, what is... I want to find out the DC biasing point of my output as well, VL. So first of all, how does one find ICQ? We're using this pathway. We know that this is a constant voltage, so this voltage across is VEB on. So through this path, I should be able to identify what is my base current, right? So the amount of base current, IB, will be determined by VCC minus VEB on, VEB on, minus 1.5 volt. That's the base bias divided by the resistance, RV. Right? So I have 2.5 volt minus, how much? This will be 2.5 minus 0.8 minus 1.5. And this will be RB. RB is 10 k ohm. Sorry, forgot to get RB here. Is 10 k. And RC here is 3 k ohm. So these are given. So we should be able to find out what is the base current first. Once we know the base current is 20 microamp. So by this biasing setup, I should be able to identify the amount of my base current. Once the base current is given, the next thing is then, what is the collector current? Collector current at quiescent point will be IB times beta. So this will give me 500 microamp, which is 0.5 milliamp. Okay? And the next thing is that you want to make sure that this device is operating inactive. Otherwise, this equation is no longer valid. So we find out what VL is. VL would then be IC RC. So this is 0.5 milliamp times 3K. This will be 1.5 volt. So this will then give us VCE equals to 1 volt, which is larger than VEC set. This is the same as VCE set. Typically, anyways, larger than VEB. So we know that it's larger than, if I want to give you numbers of VCE set, typically 0.4. Not if it's not given. So we know that it's in saturation, it's inactive. So this would then tell us that Q1 is in. Okay? So the next thing is that we need to construct a small signal model. I didn't actually spend too much time on talking about how the small signal model for MPE and the difference between the two. The reason is that it's the same. What I mean by that is that if you think about it, when I modulate, so I should be able to construct my small signal models GM B pi for a PNP transistor. Because it's small signal and it's a small signal model, so it doesn't have a direction problem, because either direction, as long as if I'm modulating this two terminal, even though it's EB modulating this, if I'm flipping the direction, it will cancel itself. Therefore, it actually had the identical model as an NPN. So If I want to construct, I'm simply insert this. This will be my emitter terminal. Emitter terminal will be ground because emitter terminal is VCC. VCC is AC ground. So if I want to construct my small signal equivalent model, I'm simply inserting the identical NPN small signal model. They are identical. NPN or PNP are identical. And then my input terminal will be this. RB. This is my small signal model, and my output terminal is collector. So collector is connected to RC. So this will then be my small signal equivalent circuit, where you can find the R pi following our previous analysis the same. So R pi GM RO can be defined based on IC or ICQ. Okay? So if I give you an early voltage, you should be able to find RO. If early voltage is not given, you can skip this part. If early voltage is infinite, then RO is infinite. So then this can be skipped. Okay? Good? I don't know if I have time for a more complicated circuit. Let's try to go through another circuit. That's even though I'm using the PNP transistor common emitter stage, but in real practice, this is very, very rare. You wouldn't use a PNP transistor for this purpose. But another circuit is probably, if you're using a pure BJT-based circuit, this will be a somewhat common circuit. So let's spend a little time on this example. So I'm going to talk about another example which PNP is used instead of an active amplifying transistor. It's used as what we call a loading device. So I want to go through another example, which is a common emitter stage. We're going to talk about this more when we talk about different type of amplifying structure. But I'm simply going to tell you when you will see a PNP transistor. This is more common than the example I used on the left. So what is a common emitter stage of an NPN? Let's say this is my transistor, Q1. This is the NPN transistor which we have already analyzed before. If you remember, I have a bias, I have a signal, and then this will be my output. Right? Remember when we deliver the circuit, we simply add a loading resistor, which is an RC, on top. But instead of having an RC, one of the things you need to understand is that in integrated circuit, it's very hard to deliver a passive component. It's very costly. So if you wanted to deliver a loading, the load simply meaning that I want to transform current into voltage. I simply use a resistor. But instead of a resistor, we're going to use a PNP transistor. So this is a PNP load. This is referred to as a PNP load. So this is called a common emitter. This is a common emitter stage with a PNP load. So this Q2 will then become the Q2 will then serve as a loading device. Okay? So this is much more common because you want to deliver all the components using transistors instead of introducing passive components such as having a resistor. So, and this will then give you additional benefit. We'll talk about that in the next chapter. But then, how does one analyze this problem? So, let's give some device parameters. IS1 equals to IS2. These are two transistors. We're assuming that it has the same IS. And beta 1 is for Q1 is 100. Beta 2 is 50. And I have early voltage VA1, VA2 equals to 20 volt. So these are the device parameters we use for the circuit. So there's two things we want to find. I want you to design VB1, VB2. Determine VB1 and VB2 so that IC1 equals to IC2 equals to 1 milliamp. So you want to set your operating point for biasing current at 1 milliamp by adjusting these voltages. And it's supposed to be balanced. The top and the bottom should be balanced itself. And then, of course, the next thing we want to know is small signal. You want to know VL versus VS, which is the AVO, the voltage gain. Open circuit voltage gain. The O stands for open because we're not adding any loading to the circuit yet. Okay? So let's see how we approach this problem. I might need to borrow maybe 5 to 10, maybe 5. Hopefully I can go fast. Okay? Let's take a look at how does one do the biasing. The biasing part is fairly simple. What we basically want to follow is the guidelines that the current should balance, the current level and the current balance itself. So VBE, VB1 equals to VBE1. We're supposed to be VT ln. If my desirable current IC1 divided by IS. This will give us about 0.78 volt. So you set it up at 0.78 based on this device parameter, it should deliver 1 milliamp. Here's inserted numbers. And of course, VB2 equals to VCC minus VCB2. And this will be 3 volt minus VT ln IC2 IS. Since IC2 is 1 milliamp, we know this is what we want. This is device parameters 10 to the minus 16. So we should be able to get this voltage level. The DC voltage level at VB2 should be about 2.2 volt. So these are just simply DC biasing, allowing the circuit to be set to its particular location, the particular level. The second part is a little bit more complicated. So we need to, when we want to do the small signal analysis, we need to construct the small signal equivalent circuit. So let me draw the whole circuit. There's 2 transistors, so it's somewhat a little bit more complicated. But let's first draw Q1. So there's R pi 1 and GM V pi. Because I have 2, so it's probably safe to keep it with that notation. Sorry. This is GM1 V pi 1. And then it's connected to a output resistance RO1. So the white part is for Q1. Let me change the color to Q2. So I have connected this to the collector. So you start with you flip the transistor and connect it to the collector. So this will be RO2. GM2 V pi 2, right? So if you look at this, this is the base. Base is connected to signal source. Use different color. So this is my input source, yes. And this is the emitter terminal. Emitter is grounded, right? And the other side of the emitter, remember this is the collector. This is collector 1. This is collector 2. So collector 1 and collector 2 are connected, right? So the collector terminals are connected, and the emitter terminal for PNP transistor are grounded, AC ground. It's VCC. So this is ground. So you can assume that they are ground. This is VCC, which is AC ground. Again, small signal. Okay? And lastly, I have this terminal connected to a R pi 2, B pi 2. And what happened to its base? Where does it go? VB2. VB2 is AC ground. It's also ground. So this is connected to ground. This is VB2, which is also AC ground. So you're grounding all the 3 DC components. The real ground, which is the emitter 1 is the real ground. And you have the AC ground of emitter 2. And this is this is base 2. And all of them being grounded. Okay? So this is my equivalent circuit. So I can quickly simplify what happened on the right is because what is V pi 2 in this case? Because it's ground, this means that V pi 2, let me use it yellow. This means that the voltage across V pi 2 equals to what? There's no small signal modulating the base current. The base voltage is fixed. So V pi 2 is 0, meaning that this is 0, this is open. So you're only seeing, you don't need the right-hand side. That's all you see. Okay? So when we look at this circuit, we can very quickly get our output response based on this circuit, based on this part. Because on the right-hand side, it only contribute RO2. The PMOS load only contribute RO2. So what happened is that you would then get your output. This is output. This common node is my output. So my VL will then become current, which is minus GM V pi 1, GM1 V pi 1 times RO1 in parallel RO2, 2 in parallel. So then this will be minus GM1. What is V pi 1? V pi 1 is Vs. So GM1 RO1 in parallel RO2 Vs. So my voltage, again, defined as the ratio between VL versus Vs, would then be minus GM1 RO1 in parallel RO2. Okay? And because we know that it has the same early voltage, RO1 actually equals the same as RO2. So we can actually do the exercise to find RO1 and RO2. Let me just get the numbers. So GM, in this case, let me write down this. So AVO here is minus GM1 RO1 in parallel RO2. Because they have the same current and the same voltage, so RO1 equals to RO2 equals to, they have the same current, so VA divided by ICQ. This will give me 20, I believe 20K. Do I have it? Yes. 20 volts, so that's 20. Okay? And then this is the same because they're the same. And GM is ICQ BT. So I can get the numbers, but I don't want it to get the final result, IC1. I'm just going to use IC1 because they're the same. IC1 equals to IC2. Okay? So if I'm simplifying this equation, this will be minus GM, GM1 times 1/2 RO, which will be minus 1/2. GM is IC1 divided by VT. RO is VA divided by IC1. The reason why I'm keeping this instead of inserting the number is because the current cancels itself. So then you get a constant ratio of minus VA divided by VT. That would be the overall gain. So the gain will depend on only two things. One is early voltage, the other is the thermal voltage. So that's your, we typically refer that into the intrinsic gain. That's the intrinsic gain of the circuit because that's what's limited by its own component, meaning that it will be depending on its output resistance and its transconductance itself. It's not depending on external resistance. It's more internal technology limited behavior that will limit your overall gain. Ultimate gain, we typically refer to that as the intrinsic gain. We're going to talk about that a little bit more. But that's just to tell you that when you will be using PNPN, what is the active load will then lead to the introduction of having a resistor contribute a resisting component or loading component that will lead to the limitation of your overall gain of the circuit. Okay? So I think I'm just going to stop right here regarding the discussion of chapter 4. So we're going to continue on more discussion on circuit analysis rather than the device part. So you leave the device part with the models, exponential model or VBR model, constant voltage model, and small signal model. We're going to use these models to bridge into the discussion of different types of circuits and how does it reflect its behavior. What do you want to deliver? So we're going to talk about, instead of only talking about amplifying, this is the most, I think the key prompt, the key performance is to deliver something called the signal amplification. Remember, we want to create a gain. The other thing you want to create is buffering signal. So we're going to talk about that a little bit more later in classes. 所以我们后面会开始讲电路的应用。那电路的应用就是除了放大以外，你可以想象，就是房子除了住人呢，还要有什么？有一些 buffer 区间啊。所以我们其实很大一部分要做界面啊，就是你在处理讯号的时候，你通常除了处理讯号，主要把讯号放大之外，其他很多的工作是你确定你拿过来的是真正的讯号，没有在这个过程中被扭曲。那这个不要被扭曲这件事情呢，就要靠非常非常好的界面。所以我们还会介绍一些界面电路，像 follower circuit，follower circuit 非常非常的好，非常非常重要，而且非常非常好用。这样子，大家如果你的手机里面有100万画素的相机，那个叫什么？100万像素，100万 pixel 的相机的话，你就有100万个 buffer。你就需要 buffer， 就所有的 sensor circuit 都需要 buffer， 所以我们会讲这个 buffer 的应用非常的重要。所以除了放大就是 buffer， 所以我们在后面会讲这些不同架构的应用跟它的 impact。好。